Today's lecture will be a review for your final exam. I wanted to make sure everyone was aware, first of all, that you are allowed to bring a sheet of your own notes to use during the exam. It can be the size of a standard notebook page, 8.5 inches by 11 inches. You can write anything you want on one side only, and it can either be handwritten or typed. So take some time to prepare that, and you can, of course, use that during the exam. So here's the basic information about the final exam. It'll be given on our last day of the summer session, which is Friday, June 27th. You can choose whatever time you want to take it during that day. It'll be just like the midterm by having a proctor, and you can choose your proctor. So I've given you some details about that in announcements, right? The proctor can either be me if you can come to campus, or you can find someone else, possibly the same person you used for the midterm. The time limit will be 2 hours. It will be cumulative over everything from this session, but it will emphasize the material covered after the midterm. So there will be some questions from earlier in the semester, but more questions will come from the second half of the semester. You could expect the questions to be similar to quizzes and homework. So that's a good place to study. Go review your old quizzes and homework. As always, I suggest that you work them from scratch rather than just reading the solutions that are already there. That will give you some practice on solving problems from scratch. So there will be no book, notes, or calculator that you can use during the exam. I will provide a formula sheet for you, and I will post that in Canvas so you can see exactly what will be on it ahead of time. You don't need to bring a copy, but I just want you to see it ahead of time. And then just like the midterm and quizzes, you always need to show all of your work in order to make sure you can earn full credit. I made a list here of the sections that are covered on the final exam, and it's basically, this lists all the sections we've covered for the whole session, but I separated them out into pre and post midterm. So in pre-midterm we covered chapters 2 and 3, so chapter 2 on limits and derivatives, chapter 3 on the differentiation rules. So there will be a small part of the final exam that takes questions from those chapters. And then post-midterm is on chapters 4 and 5. So here we looked at applications of differentiation and integrals. And so that will be the majority of your final exam will be on those two chapters. As I mentioned a minute ago, there will be some questions that come from material before the midterm. I'm not going to review that in this lecture. You can see the review that I posted earlier. It's the June 11th lecture where I did a review there for the pre-midterm material. So another thing you can do as you're studying for the pre-midterm material is go back to those quizzes and homework and also review the midterm itself. The problems will be similar to those types of problems. And as always, make sure you're working problems from scratch rather than just reading the solutions. So the rest of this review will be on material presented after the midterm. Now I'm going to go through the 2 chapters that are post-midterm and talk about the different types of problems that you're expected to be able to do. So we'll start with chapter 4 on applications of differentiation. So one thing you need to be able to do is find critical numbers. Right, so the specific method for that is take your function, compute its derivative, and then you have to look at 2 situations, either where f prime is equal to 0, or, well, I should say and, any points that make the derivative undefined. Any values of x that do either of those things, those x's would be critical numbers. And remember, the importance of critical numbers is to help us find local extrema, which we'll get to in just a minute. So the second type of problem, be able to use the closed interval method to find absolute extrema. So make sure you're aware, first of all, the difference between local and absolute extrema. Local max looks like a mountain peak or a mountain corner, right? Local min looks like a valley bottom. Absolute, and there can be many local extrema to a given function. Absolute extrema is only the absolute highest and lowest points. Now there can be ties, but in often cases there's just one of each. Right? So the absolute also can occur at endpoints, whereas that can't happen with local extrema. They can never be at an endpoint. Okay, so review the differences between local and absolute. Now here, the closed interval method was the way that we found absolute extrema. So there were several steps involved in this process. Basically, you make your list of candidates, and the candidates come from 2 places. All the critical numbers are candidates, and the 2 endpoints of your interval. Okay, so this problem only applies if you're looking at a function over a closed interval, so you'll have 2 endpoints. Once you have your candidates, you just substitute them into your function. And then you compare. You look at all the outputs. The absolute biggest output, that tells you you've got your absolute max. And your absolute smallest output tells you that's your absolute min. Okay, moving on, finding intervals where a function is increasing and decreasing. So the method we learned for that was called the first derivative test. And this was another use of our critical numbers, but we only use, so you take your critical numbers and you put them on a number line in order from smallest to biggest. So I'll just say here, use a number line. I'm not going to write out all the details of this step, but basically you put all your critical numbers on the number line. That creates subintervals. You choose a test point from each subinterval, and you substitute each test point into the first derivative. And all you're interested in is whether the first derivative is positive or negative. If f prime is positive, it tells you f is increasing. If f prime is negative, it tells you f is decreasing. And that gives you your intervals that you can read off the number line. Next type of problem, find local extrema. And you use the work you just did, finding the intervals of increasing and decreasing. That tells you where your local extrema are, right? If it switches from increasing to decreasing, you've got a local max. If it switches from decreasing to increasing, you've got a local min. Now there's another method for finding local extrema that we'll get to a little ways down our list. Next point, find the intervals of concavity. So where is a function concave up and concave down? The test we used for that was called the concavity test, and that method is almost identical to the test for finding increasing and decreasing, the first derivative test, except instead of plugging into f prime, you substitute into f double prime. Okay, so I guess I should also mention the numbers you put on your number line are values that make the second derivative equal to 0. So it's not the same as the critical numbers. So you find the values where f double prime equals 0. These values go on the number line. And then when you pick your test points, you substitute them into f double prime. And wherever f double prime is positive, you know the curve is concave up. And when f double prime is negative, you know the curve is concave down. And then related to that, our next point is finding inflection points. So inflection points are the x values where concavity changes. So if you look at the number line you made using the concavity test, if you have a point where you change from concave up to concave down or vice versa, that x value would be considered an inflection point. Now our second method for finding local extrema, right? We have two methods, one here, one here. They both involve finding critical numbers. It's just how you test the critical numbers that's different. So using the second derivative test, you plug your critical numbers into f double prime. And then if f double prime is positive, you envision concave up, and that shows you have a local min at that critical number. If your second derivative is negative, you envision a concave down curve, and that tells you you've got a local max. Okay, so sometimes one test is easier to use than the other. If you've already made a number line to determine the intervals of increasing and decreasing, you might as well use the first method because you can read it directly from that. But if you haven't gone to all the effort of creating the number line, it might be easier to use the second derivative test. And then the last point mentioned here is curve sketching using derivatives. So this is a really nice application of several of the things covered in this chapter. It kind of puts everything together to help you sketch the graph of a function. So you have to find, the intervals where it's increasing and decreasing. Find the local extrema. Find the concavity intervals and the inflection points, and then put all that together to create a graph of a function. And you sometimes have to consider some extra things that are not just calculus, such as vertical asymptotes, horizontal asymptotes, domain issues, and intercepts are often useful, finding x and y intercepts. All of those last few things I mentioned are things that you learned in pre-calculus. Got a few more topics from chapter 4. Some other problems you need to be able to do. One is evaluating limits that have indeterminate forms. And in almost all of these cases, it involved using L'Hopital's rule at some point. So make sure you're aware with what the various indeterminate forms are. There are only two indeterminate forms where you can use L'Hopital's rule, and that is what we call 0 over 0 or infinity over infinity. Okay, so be able to, if you have a limit with one of those two forms, be able to apply L'Hopital's rule to help evaluate it. There are other indeterminate forms where you can't use L'Hopital's rule, such as infinity minus infinity or 0 times infinity, and there were some powers also. There were like 3 different indeterminate powers, right? So there are these other indeterminate forms where they're not in the right form to use L'Hopital's rule, but you can do some manipulation with these to get them in a form where you can use L'Hopital's rule. Okay, moving on to the next one, we had a whole section on optimization problems. So these are basically word problems where you're asked to find the best or the least expensive or the smallest something or biggest something, right? So look for those words that tell you you're dealing with an optimization problem. And the basic outline of our strategy is you need to create a function for the thing you're trying to optimize. Right, so if you're trying to minimize area, you need an area function. If you're trying to maximize profit, you need a profit function. Once you develop that function, you have to make sure that it's a function of only one variable. So sometimes you have to do some work to rewrite your function until it's in terms of one variable only. And then once you have that, you apply our methods of finding absolute extrema. And if it's asking you to maximize, look for the absolute max of your function. If it's asking you to minimize, look for the absolute min. And often these are over closed intervals. And the intervals are usually not given, right? You have to identify the appropriate closed interval in the context of the problem. And then the last topic from chapter 4 is to be able to find antiderivatives of a function. And we usually express that as finding a general antiderivative. And that means you start by finding one antiderivative and then you just put plus c at the end. And now you have a list of all of the antiderivatives, which we call the general antiderivative. So now moving on to chapter 5 on integrals. We only covered 3 sections here. You'll pick up with the rest of it in Calculus 2. But here's a list of the topics that we covered. So one thing you need to be able to do is if you're given a function in a closed interval, estimate the area below the curve down to the x-axis using rectangles. And so the problem might tell you how many rectangles to use, and it might tell you how to determine the heights of each rectangle. The usual methods we use for determining the height are either left endpoints, right endpoints, or midpoints. And so that involves setting up the rectangles, calculating their areas, and adding them together. Second point, be able to estimate distance traveled if you're given periodic velocity readings. So this is relating to the distance problem, right? The first problem addressed here is the area problem. And then the second bullet here is talking about the distance problem. And what we showed in this section is they're essentially the same problem. It's just one is in the context of a moving object. Because we discovered that if you have a graph of a velocity function, the distance traveled is just the area below that velocity curve. Third point, calculating a Riemann sum, but that's really the same as the first point, estimating an area using rectangles. It's just the way the question is asked that's different, but the actual calculations are the same. So whichever way the question is posed, be able to recognize it's asking you to do the same thing, basically. A Riemann sum comes from the idea of adding up areas of rectangles. Then we have using properties of integrals to help evaluate definite integrals. So these are things like if you're integrating a sum or a difference, that you can split the integral up over that sum or difference. Or if you have a constant times a function that you're integrating, you can pull the constant out in front of the integral sign. Okay, those are some of the properties. Also, if you're integrating from a to a, right, from one number to the same number, that value of that integral will always be 0. And also, what happens if you switch the order of the limits of integration? So if you switch and you integrate from b to a, that's the negative of the integral from a to b. Those are some of the properties. Then I have a separate list here, use the comparison properties of integrals. Now there are various things you could use them for. one example of using these is estimating the value of a definite integral. Okay, so we had, it was the last comparison property we listed, gave you a way to estimate. So you can review that. And then the last 2 points are on the fundamental theorem of calculus. It had 2 parts. Part 1 gave us a method for finding the derivative of an integral function. Now remember what an integral function is. We usually called them g of x, and they were defined this way. The integral from a fixed constant a to a variable x, and then the function you're integrating, f of t, and then we always have a dt with our integral sign. So fundamental theorem part 1 tells you how to take the derivative of a function like this. And the idea is the derivative will undo this integral and you'll get this function back. And then the fundamental theorem part 2 can be used to help evaluate definite integrals. And this will be extremely useful to you as you go forward into Calculus 2. It makes it much easier to evaluate many integrals. So the idea is, right, if you're given a definite integral that you want to evaluate, you start by finding any antiderivative of little f, which we usually call capital F. And then we put this vertical bar to indicate what you have to do with that antiderivative is first plug in the right endpoint, then you subtract, and you plug in the left endpoint. So that covers all of the topics from chapters 4 and 5. So now we'll spend the rest of this lecture doing some sample problems to practice with some of these ideas. Here we're given a function and asked to find the intervals where it's increasing and decreasing, and then also find the local extrema. So this is where we use that number line method, and we start by finding the critical numbers because those are the numbers we put on the number line. So to find critical numbers, we need the first derivative. Now notice f of x has a square root, so to take the derivative, we always rewrite the square root first as a 1/2 power. So here I'm just rewriting the function f. Now let's take the derivative. So this will be a chain rule problem. The outer function is the 1/2 power function, so we start with that derivative using the power rule. Bring the 1/2 down in front. Reduce the power by 1, so 1/2 minus 1 is negative 1/2. And then we multiply by the derivative of the inside part, which is 2x. Notice the 2's cancel. And so we could bring that negative exponent down to the denominator. When we do that, all that's left in the numerator is x. And then in the denominator, we'll have x squared minus 1 to the positive 1/2, and we could rewrite that 1/2 power back to a square root. Okay, so that's f prime. Now we need to look at 2 things for finding critical numbers. First of all, values of x that make f prime equal to 0. And then second, values that make f prime undefined. Let's start with equal to 0. So if we set this whole expression here equal to 0, the only way any fraction can equal 0 is if the numerator is 0. So you really just have to set the numerator to 0, which is x equals 0, and that's already solved for x. So we get x equals 0. So that's one critical number. Now let's look at values that make the derivative undefined. So because we have a fraction here, this would be undefined if the denominator were 0. And so you want to think what values of x would make the denominator equal to 0, and that would be either 1 or negative 1. So we have two more critical numbers. Now this first derivative would also be undefined if the expression under the square root were negative. And that brings up a point. If we look back at the original f, it might help if we discuss the domain of f, because we want to make sure the critical numbers we pick are at least in the domain. So let's work on this for a second. So because f of x has a square root in it, we know that it's only defined if the expression under the square root is 0 or bigger. So this is defined if the x squared minus 1 is greater than or equal to 0. So then we want to solve this for x. So this tells us we have x squared greater than or equal to 1. And you have to be careful with inequalities if they're nonlinear, like this one has an x squared, so it's nonlinear. You can't just take the square root of both sides to get the solution for an inequality. You learned a whole method for this in pre-calculus, but this one is simple enough we can just kind of reason through it. So if we were to solve this for x and think about what x's would satisfy that, it's pretty clear that any x greater than or equal to 1 would satisfy it, right? If you take any number greater than or equal to 1 and you square it, that number would be greater than or equal to 1, meaning it would satisfy this. But there are also some negative values that work, and that is x less than or equal to negative 1. For example, if you chose x equal to negative 2, which is in this interval, when you square that you get 4, which satisfies that it's greater than or equal to 1. So the only values that are a problem are values between negative 1 and positive 1. For example, 0, right? If you plug 0 in, you get the square root of negative 1, which is undefined. Okay, so to describe our domain here, we could put it in interval notation. It's all numbers less than or equal to negative 1, that's this interval. And then it's also the interval from 1 to infinity. So notice the critical numbers we found. One of them is x equals 0. That's not even in the domain. So we shouldn't even consider this one. Okay, so we throw that one out. But the other two, plus minus 1, they are in the domain. So those are the only ones we need to consider in as we move forward. So we're ready to make our number line. We put our critical numbers on it. And we also want to mention that this part is not in the domain, so we don't need to plug in anything there. Okay, so we've got two intervals to consider. We'll use our test point method. So let's choose negative 2 for that interval and positive 2 over here. Now we take our test points and we're going to plug them into f prime because it's the sign of f prime that tells us about the function increasing and decreasing. So let's find our formula for f prime. This was it right here. So usually we write that in factored form, but for this case I don't think we'll really need to do that. The square root kind of complicates things. So the formula for f prime is just x over the square root of x squared minus 1. So when we plug negative 2 in here, the numerator will be negative. Now the denominator will always be positive because the square root it's a function that's defined always to give you the positive square root. Notice when you plug it in, you'll get 4 minus 3 underneath, so it's the square root of 3, that's positive. So it's a negative over a positive. So combined together, that will give us a negative. Our other test point is 2. when we plug 2 in here, the numerator will be positive. Denominator will be square root of 3, which is positive. Okay, so we have positive over positive, which of course is a positive result. So then those signs tell us about increasing, decreasing. So the first subinterval on the left, we have a negative derivative, which means the function is decreasing. And then the subinterval to the right of 1, f prime is positive, which tells us the function is increasing. So our answers here, we could say the function is increasing on the interval from 2 to infinity. And, or sorry, 1 to infinity, right? That's a common mistake. You don't want to make that mistake. You never use a test point as your endpoint, right? The endpoints always come from the critical numbers that you put on the number line. Okay, so back to our problem. Decreasing is negative infinity up to negative 1. So then what about local extrema? So normally what we're looking for is where the graph changes from decreasing to increasing or vice versa. And we do have a change here, but there's a gap in between. All right, so if you wanted to kind of visualize what this graph looks like, very roughly, it starts out decreasing until we get to negative 1. I guess I need to mark negative 1 and positive 1. So it's decreasing. We don't know exactly how, but it's decreasing as it approaches negative 1, and it's defined at negative 1, so it's not an asymptote. And then it jumps. There's nothing in between negative 1 and positive 1. And then to the right, it's increasing. So there's no asymptote, it's just a jump. So there's no local max or min here, right? Because the two pieces aren't connected, right? If this switch had happened right here, decreasing to increasing, we would have a local min at negative 1. But because of the jump, we don't have any local extrema. All right, so that was a little practice with using the first derivative test to determine where a function's increasing and decreasing, and then analyze the results to determine where you have local extrema. We're asked to find the absolute extrema this time, not local, for this given function over a given interval. So usually for finding absolute, we use the closed interval method. And also you can only use the closed interval method if you're looking over a closed interval. And notice here, this is our closed interval. If you were asked to find absolute extrema with no interval given, then you can't use this closed interval method. You'd have to think about it in a different way. Okay, so for the closed interval method, one thing we need are the critical numbers. Okay, so for that we need the first derivative, and this one has a very simple derivative. It's 0 minus 2x, so just minus 2x. And then we look for the two situations. One is f prime equals 0, the other is f prime undefined. Okay, so f prime equals 0, you would just take your f prime formula, set it equal to 0, and solve for x. We get x equals 0, so there's one of our critical numbers. And then for f prime being undefined, notice f prime is just a linear function that's defined everywhere, so we're not going to get anything from that. So we only have the one critical number. Now we're not going to use the number line method. That's for finding local extrema. What we do now is we list our candidates. And the candidates always include all of the critical numbers and the endpoints, which are -3 and 1. And when you write out these candidates, you need to also check to make sure all the critical numbers you're listing are actually in this interval. So if we had found, say, 3 as a critical number, notice 3 is not in this interval, so we would throw it out because we're only looking at the graph over this interval. Now our critical number 0 is in this interval, so we're going to keep it. And then all we do is we evaluate the original function at all of our candidates. And then we'll compare the results. So f of 0, go back to your formula here, will just be 4. F of negative 3 will be 4 minus, negative 3 squared is positive 9, so it's 4 minus 9, which is negative 5. And then f of 1 will be 4 minus 1, which is 3. So now we look at our 3 results. Find the largest of these, which is the 4. So that tells us we have an absolute max. Now be careful how you present the results. It depends on how the problem asks for it. Or if it's unclear, then you might want to just give all the information. So here it just says find the absolute extrema. It's not very clear, so let's give both. So if they ask for the values, that's the y coordinate, which here is the 4. And if they ask where they occur, they want the x coordinate of the point. So this one occurs at x value 0. Now look at all of our outputs and find the smallest. That would be the negative 5. So this one has an absolute min, and the value would be negative 5. And it occurs at x value negative 3. Okay, and that's it. And if you wanted to get a picture of this just to see if it makes sense, you could. This is an easy function to graph. We took y equals x squared. The negative flips it upside down, so this upside down parabola with vertex at the origin. And then adding 4 shifts it up 4 units. So it's going to cross here at 4 and have an upside down parabola. And we're looking over the interval from negative 3 to 1. So notice it crosses here at 2 and negative 2. It's easy to find the x-intercepts from the formula. So negative 3 is out here, so it's kind of hard. I'm running out of space. 1 is here. So we're really just looking at this piece. And you can see here the absolute max. And does that correspond with what we found? Right, we found absolute max value is 4, which occurs at x value 0. That's exactly what this is. We're at height 4, and it corresponds to an x value of 0. The absolute min value we found, we said it occurred at negative 3. You can see it right here. That's definitely the min at this left endpoint. And you can see it occurs at x value negative 3, just like we said. And then the y coordinate there is negative 5, which you could get by plotting points like we did here. So the picture here corresponds to the results we found using the closed interval method. Here we want to find the intervals of concavity for this given function. So for concavity, we need the second derivative. So we'll start by finding g prime. Just a power rule problem, so we'll get 12x squared minus 4x cubed. And then take the derivative of that to get g double prime. So that will be 24x minus 12x squared. Okay, so now this is just like finding critical numbers, except we use the second derivative. So we're going to look for the two things, values that make g prime equal to 0 and values that make double prime undefined. So for the first one, take our formula for g double prime, set it equal to 0, and then we'll solve for x. Now you might be tempted to divide by x, right? Because that would cancel out some of the x's we see there. But you never want to divide by a variable if it could potentially be 0, right? And for example, x squared plus 1 would not be 0, so it's fine to divide by x squared plus 1. But x is a variable, it could be 0, so we can't divide by x. So we need to factor instead. And if you want, you could also factor out 12 from each term. So we'll factor out 12x. From the first term, the 24x, that leaves 2. And from the second term, it leaves minus x. So now we've got a product equal to 0, so we set each individual factor equal to 0, and then solve each one of those. From the top one, we get x equals 0. From the bottom one, we get x equals 2. So here's two critical numbers. Now let's look at values that make g double prime undefined. Well, notice g double prime is a polynomial. It's defined for all x, so nothing here. So we've got two critical numbers, so we put those on our number line in order. Choose test points. Notice here there's no domain issues. G is defined for all x. Right, in a previous example, we had a function that was not defined for all x, so we had to cancel or mark that part off on our number line. So now we'll choose our test points. So I'm going to choose -1, +1, and 3. And then we're going to plug those into g double prime. And if you can factor it, that always makes this easier. And notice we did factor g double prime right here. Okay, so if you write a factored form, make sure it matches exactly what's here. Sometimes when you set this equal to 0 and you start solving, that's fine for solving, but if you say divide both sides by 12, it's not the same function anymore. So make sure your factored form is exactly the factored form of what you see here. And it is in this case, right? So I'm going to write the factored form here so I know I can see where I'm plugging in. Okay, let's take our test point -1. When we plug it in here, we get -12. And then in the parentheses, 2 minus -1, that's 2 plus 1. So the first factor was negative, second factor positive. So that product will be a negative number. Our next test point is 1. And the first factor will be 12, which is positive, and then 2 minus 1, which is positive. So both factors are positive. So that gives us a positive result. And then substituting in 3, this term will be positive, and then the 2 minus 3 will be negative. So a positive times a negative gives us a negative result. Now this was in the second derivative, so it tells us concavity, right? So minuses mean concave down, pluses mean concave up. And so then we can write out our solution. Concave up, we'll do that one first. There was just the one interval from 0 to 2. And then for concave down, we had two intervals. Everything to the left of 0, and then everything to the right of 2. And that's all we were asked to do with this one, was to find those intervals of concavity. Oh, there was one other thing. Find inflection points. So looking back at our number line, look for any points where the concavity changes. And notice we had one here at 0, changed from down to up, and we had another at 2 because it changed from up to down. And usually we give our inflection points as ordered pairs. Okay, so one of them has x-coordinate 0. Now to find the y that goes with it, it's just like plotting points. Make sure you go back to the original function, not to g prime or g double prime. And plug 0 in to get the corresponding y value. So that's clearly going to be 0 for y. And then the other one has x coordinate 2. So to find the y coordinate, we plug 2 in here. So 4 times 8 is 32. And then minus 2 to the 4th, which is 16. So 32 minus 16 is 16. And that's our those are our only inflection points. And so now we're done with this example. This is a curve sketching example, so the parts A through E are leading us through all the steps for all the pieces we need in order to sketch this curve. But if you look at the formula x minus sine x, this is not an obvious graph, right? We couldn't just easily figure out this graph using transformations. So we're going to use our calculus methods to get a good picture of this graph. So part A starts with finding the intervals where it's increasing and decreasing. Right, so we practiced one of these earlier. For that, we need the critical numbers, and to find critical numbers, you need the first derivative. So let's go ahead and calculate f prime. Derivative of x is 1, and then we have minus the derivative of sine is cosine. So to find our critical numbers, we look at two things: values that make f prime equal to 0, values that make f prime undefined. So take our formula, set it equal to 0, solve for x. So first thing we do is we get cosine x equals 1. Now we have to use some of our trig knowledge to think about values of x, which is like the angle, find the angles that have a cosine value of 1. So if you visualize your unit circle to help with that, cosine is always the x-coordinate of your ordered pair. So we want to find points on the unit circle where the x-coordinate is 1. And there's only one point, it's right here, the point 1, 0. And that angle is 0. So we get as a solution x equals 0. But remember, with trig equations like this one, cosine x equals 1, if there's one solution, there's always an infinite number of solutions. And so you have to remember that if you go multiple times around the circle, as long as you end up back at the same point, the cosine value will still be the same. It will be 1. So going around the circle means adding 2 pi, or you could go around twice, add another 2 pi, or another 2 pi. So if you add any constant multiple of 2 pi, you get a solution. So we don't need to write the 0. We can just say x equals 2 pi times k, where k is any integer. So we have actually an infinite number of critical numbers from that part. We still have to look at the f prime undefined. If you look at the formula for f prime, right, cosine is defined for all x. So this is always defined, so we're not going to get anything from the second case. But we still have an infinite number of critical numbers to deal with. So we obviously can't put them all on a number line, but since this is a periodic type function, we can just find a pattern. So let's make our number line and list some of those critical numbers. So if k is 0, we get x equals 0. If k is 1, we get x equals 2 pi. If k equals 2, we get 4 pi. Right, and then it just continues like that forever. But there's also, we need to show it goes in the negative direction. So if k is negative 1, we get negative 2 pi. If k is negative 2, we get negative 4 pi. Right, it continues forever. Okay, so let's start picking test points. So let's start way off on the left. Well, let's start actually just to the right of 0. Pi would be a good choice because we know that's between 0 and 2 pi. And then to the right of that, a number that we know is between 2 pi and 4 pi would be 3 pi. Now let's go to the left. We could choose negative pi for this one and negative 3 pi for this one. I think that's enough, right? You could put another one over here, but it doesn't go forever. So I think we'll just leave it at this and hope that's enough to see the pattern. Now we're plugging these in to the first derivative to determine increasing, decreasing. Our first derivative formula was just 1 minus cosine x, and there's no way to factor that, so we'll just plug it in like that. Okay, let's start. How about on the right with our test point 3 pi. Cosine of 3 pi is negative 1. So we have 1 minus negative 1, which is 1 plus 1 or 2, so positive. Let's plug in pi. Cosine of pi is negative 1. So we have 1 minus negative 1. Same thing, positive. Continuing with this example, the next step is to find the intervals where it's concave up and concave down. For that, we'll need the second derivative. So here I've copied the function that we were given and f prime that we calculated. So now let's use the formula for f prime to find f double prime. So the derivative of 1 is 0, and then we have minus the derivative of cosine, which is negative sine. And then the two minuses make this sine. Okay, so we're on part C. So for concavity, remember this part is just like finding your critical numbers, except you use the second derivative. So we look at two things, values that make the second derivative 0 and values that make the second derivative undefined. So take our formula for f double prime, which is sine x, set it equal to 0, and solve for x. Again, we need to use some trig here. Find all angles that result in a sine value of 0. So on our unit circle, remember the sine value is the y-coordinate of your point. So we want to find points on the unit circle where the y-coordinate is 0, and there are 2 points that have that. 1, 0 over here, and negative 1, 0 over on the left. So we want to find the angles that correspond to those 2 points. So this point here is clearly at angle 0, and this one could be angle pi, right? Half of a rotation is pi. And then if you keep going, you get 2 pi. Continue on, 3 pi, 4 pi, 5 pi. You can also do that in the negative direction. So notice we're getting all multiples of pi. So any integer k times pi. So infinite number of critical, not critical, but analog to critical numbers. Now let's look at values that make the second derivative undefined. Well, f double prime is sine of x, and it's defined everywhere, so we don't get anything from that. So now we take all of our numbers we found, the k pi's, and put them on a number line. So we can't list all of them because there's infinite number, but just list a few to see the pattern. So if k is 0, we get 0. If k is 1, we get pi. If k is 2, we get 2 pi. And then 3 pi, and so on. Let's list some in the negative direction. If k is negative 1, we get negative pi. If k is negative 2, we get negative 2 pi, and so on. Okay, so then we'll choose test points in each subinterval. So I'm going to start at 0 and go to the right first. So between 0 and pi, we could choose pi over 2. Between pi and 2 pi, I could choose 3 pi over 2. Next one could be 5 pi over 2. right? That's like 2.5 pi. Let's go to the negative range now. So how about negative pi over 2, negative 3 pi over 2? So you can see the pattern. It's always an odd number times pi over 2 is what we're using for our test points. Now we want to plug all these into the second derivative, which is a very simple formula. F double prime is sine x. So that's what we're plugging into. So when we plug in, let's start with pi halves, one of our test points. Sine of pi halves is 1, so that's positive. Let's go to 3 pi halves. Sine of 3 pi halves is negative 1, so we got a negative there. Now 5 pi halves is back up at the same location as pi halves on the unit circle, so you'll get the same result, positive 1. Now let's move to the left. Our test point negative pi over 2, that takes you to the bottom half, this bottom location on the unit circle. The y-coordinate there is negative 1, so sine is negative 1. Negative 3 pi over 2 takes you up here. Y-coordinate 1, so sine is positive 1. So you can see it's alternating plus minus. So that tells us the concavity, right? The pluses are concave up, minuses concave down. And it will continue alternating like that infinitely on either side. Okay, so our conclusion about concavity. Concave up on, let's see, we have starting on the left the interval negative 2 pi to negative pi. The next one was 0 to pi. The next one was 2 pi to 3 pi. And it will continue forever, and it will continue forever to the left also. So that's just a few of the pattern of the intervals. Concave down, the first one we listed was negative pi to 0. And then there's another one at pi to 2 pi. Right, if we want to include one more, we didn't write it here, but you can figure out, right, this next one would be concave down, and it would go 3 pi to 4 pi. And then we'll just note that it continues on in both directions. Now let's list our inflection points. So every point we marked here turns out to be an inflection point. Sometimes they're not, right? If you have two pluses in a row, the point in between would not be an inflection point. But here it changes concavity at all of these. Normally we list these as ordered pairs, but I think that's going to take a little too long. Let's just list the x-coordinates. Notice it is all the multiples of pi, k pi. If you wanted to find ordered pairs, just do the same as always, right? So plug in, like if you took x equals 0 as one of those, plug that in up here, get your y-coordinate that goes with it. So we may do some of those when we graph it. And that's, we just answered part D here with the inflection points. So now all that's left is to create the graph. So we'll do that on the next slide and we'll put everything together. Now we're going to create the graph of this function. I summarized some of the results we found earlier, and we'll consider those as we create this graph. So I'll make my axes. Now when I label my marks on my x-axis, look at the important points. So there were no local extrema, so we don't have to consider those. Our intervals of increase and decrease, it's always increasing, so that's not much to do about that. Concavity, though, notice it changes at every multiple of pi. So we'll want to show several multiples of pi so we can see those changes. So I'm going to mark off pi, 2 pi, 3 pi, 4 pi, and then we'll have some negative. Now we haven't found any y values. It might help if we find at least the y-intercept. X-intercepts might be kind of harder to find. So the y-intercept is always easy to find because you just plug 0 into the function. And so we'll get 0 minus sine of 0, which is also 0, which is 0. So we've got this point 0, 0. Maybe we should plot at least one or two more points because we have nothing else with y-coordinates on this one. So if you just make a table like you're plotting points, maybe we could plot some of our inflection points. So remember we found those and they came from here. Notice at every multiple of pi, that's where the concavity was changing. So let's plug in, say, pi, maybe 2 pi on our table. We can do some more if we decide we need to. So when you plug pi into your function, you'll get pi minus sine pi, but sine of pi is 0, so it's just pi. When you plug 2 pi into the function, you get 2 pi minus sine of 2 pi, but sine of 2 pi is 0, so it's just 2 pi is what that simplifies to. Notice at every multiple of pi, you're just going to get that number back, right? Because sine is always 0 at a k pi. Okay, so let's mark off some points on our y-axis. Let's go up to 4 pi. And we'll show some in the negative direction. Okay, so let's plot these other points we found. So we had pi, pi, 2 pi, 2 pi. Notice we'll get 3 pi, 3 pi, 4 pi, 4 pi. When we choose x negative pi, right, the y output will be negative pi. And then negative 2 pi comma negative 2 pi. Right? If you just plotted those points, you might think this graph is a straight line. But we know the concavity is changing regularly, so we know it's not a straight line. It does fit the description of being always increasing, right? That looks correct from the points we plotted. Now to get the concavity, what I usually do is I put a number line at the bottom. I usually put 2 number lines, one for increasing, decreasing, and another for concavity. But here, because it's always increasing, we don't really need the one for increasing, decreasing. Now the concavity, we had it changing at every multiple of pi. So I'm going to put those marks directly below their locations on the x-axis above. And looking at our intervals here, concave up was like 0 to pi, and then, which is here, and then it skipped. The next interval, pi to 2 pi, was concave down, and then 2 pi to 3 pi was concave up. So if you remember when we did this, they were alternating over these intervals marked off by multiples of pi. Okay, so let's start sketching our curve. It needs to pass through all those points we plotted and make sure it stays increasing all the time. And then if we start here, we want it to be concave up at first. You have to make sure it doesn't decrease though, right? It's easy to want to make it concave up, to make it go down and then up, but it can't. It has to always increase, but slightly arced in the concave up manner. And then once we get to this red dot, we switch to concave down, but it stays increasing. Okay, so let's see if we can fill in that part. Increasing concave up at first. And then here switches to stay increasing, but now it's concave down. And then you can just follow that same kind of shape over and over. So switches to concave up, concave down, concave up, concave down, and it continues like that forever. So here's our graph of f of x, which is x minus sine x. Right, we expected it to have some kind of wave to it because of the sine function, but having this x here kind of changed things, and now, without doing this analysis, we wouldn't really know what this graph looks like. Okay, so all kinds of different things could happen in these examples, right? Usually we have different intervals where it's increasing and decreasing, but here it happened it was always increasing. So be able to recognize when different things happen and just include them in your analysis the way that you always think about those things. We're asked to evaluate a limit. Now with limits, we always try direct substitution first. Unless it's a piecewise function, then you have to consider one-sided limits. But this is not a piecewise function, so we always try direct substitution first and see what happens. If it's defined, when you use direct substitution, then that's your limit, right? Assuming it's one of our familiar type functions that's not piecewise. That's what we usually conclude. Now here, when we plug in 0 for x, notice the numerator will be sine of 0, which is 0, and then minus another 0. So the numerator is 0, and the denominator will be 0 cubed, which is 0. Right? And the reason I plugged in 0 is because the limit is as x approaches 0. So when we plugged in, we got something that's undefined because of the 0 in the denominator. But that doesn't mean the limit doesn't exist, right? It's still possible that the limit could exist. But notice we would call that 0 over 0 the form. And that's a form where you can use L'Hopital's rule. So that's what we're going to do. So we're going to take the given limit, and L'Hopital's rule has you rewrite it as a new limit. In the numerator, you take the derivative of the original numerator. So the derivative of sine is cosine. And then we have minus the derivative of x, which is 1. In the denominator, derivative of x cubed is 3x squared. So now we have a new limit, and we see if we can evaluate it. So we always try direct substitution first. The numerator will be cosine of, we're plugging in 0, right, because x is approaching 0. We'll have cosine of 0, which is 1, and then we subtract 1, so it becomes 0. Denominator, 3 times 0 squared is 0, so again, undefined. But it happens to be that same form, 0 over 0, where we can use L'Hopital's rule. Okay, so we're going to try using L'Hopital a second time. Okay, so we rewrite our limit as a new limit. In the numerator, we take the derivative of cosine, which is negative sine, minus the derivative of 1, which is 0, so I don't have to write that. And in the denominator, the derivative of 3x squared is 6x. We have a new limit. We always try direct substitution first. Well, in the numerator, we get negative sine 0, which is 0. Denominator 6 times 0, which is 0. We're getting a pattern here, right? Again, it doesn't exist, so that doesn't tell us a limit. And I should also mention these forms we're getting are indeterminate forms, right? If we got something like 1 over 0, that's a determinate form. We could automatically conclude the limit is infinity. Or if we got 0 over 1, that's defined, right? So that limit would be 0 over 1 is 0. But we're getting indeterminate forms, and it happens to be one of the indeterminate forms where we can use L'Hopital's rule. So same thing, we have this form 0 over 0, which tells us we can use L'Hopital a third time. Okay, so we rewrite our limit as a new limit. In the numerator, we have a negative sign, and then the derivative of sine is cosine. Denominator, derivative of 6x is 6. When we try direct substitution this time, we get, in the numerator, negative cosine of 0, so that's negative 1, over 6. This is defined. So that is our limit. Negative 1/6. Okay, so it does often happen that you have to use L'Hopital's rule repeatedly before you finally get to a limit you can evaluate. Sometimes the process could go on forever and you'll never get to a solution, but we could tell this one was eventually going to get us somewhere because every time we use L'Hopital's rule, it decreased the power in the term in the denominator, so eventually it became a constant, and that's when we stopped getting 0 in the denominator. Let's read through this problem first. We have a 216 square meter rectangular plot to be enclosed by a fence and divided into 2 equal parts by another fence parallel to one of its sides. What dimensions for the outer rectangle will require the smallest total length of fence, and then also how much fence will be needed? So here we can first recognize that this is an optimization problem because look at the word smallest. So this tells us this is an optimization problem. And let's go ahead and think about what we're trying to optimize. We want the smallest length of fence. So we want, smallest means minimize. We want to minimize the length of fence. So we know that one of the major steps of this problem is to find a function for the length of fence. And once we have that function, we will find the absolute minimum. Let's go ahead and make a picture of what they've described here. So we're making a rectangular plot, and it's going to be divided into 2 equal parts. So we could either put it at the midpoint this way or the midpoint this way, but for the picture it doesn't matter, right? Let's just say this way. But we do have to make sure the 2 halves are equal. Now, what are we told? The area inside the entire thing is 216 square meters. And that's all we're told. We can start labeling pieces now. So why don't we call notice that one of the questions asked us to find the dimensions of the outer rectangle. So let's give letter names to those dimensions. So let's let x be this total length here, and then y will be this other dimension. So those are 2 of the pieces we're asked to find. What should x and y be? We could also go ahead and label these smaller pieces here would have to have length x over 2. Okay, so we had a whole strategy for these types of problems, and the first parts we've kind of done. It's, read through the problem till you understand what they're asking, and then start naming variables and labeling them on your figure. Right, so we get to pick the dimensions, kind of what they're asking. We need to pick what should the length of x be and what should the length of y be to get the minimum possible amount of fence, right? The area is fixed. We have to construct it so it has this area. But when you add up all these pieces of fence, we want that to be a minimum. Okay, so we've already identified kind of our first goal is to find a function for the length of fence. And you can name that function whatever you want. Let's just call it f of x. Okay, so we're trying to minimize the total amount of fencing used, so we have to include all of it, even that subdividing piece. So if we add up all these lengths, we have x plus x, so that's 2x, and then y plus y, which is 2y, but then there's another y here, right? So it's actually 3y. So the total fence will be 2x plus 3y. Now this often happens with these types of problems, that our first attempt at this function, we have too many variables on the right side. We need it to be a function of one variable only, but our expression has two variables in it, x and y. So we need to eliminate either x or y. And to do that, we need a new equation that's completely different from the one we just wrote. So it doesn't have anything to do with the length of fence. So here's where to get your other equation, you can either get it from your figure using some kind of geometric argument, or if there's any information you haven't used yet, that you have to use that at some point. And here we haven't used the area being fixed at 216 square meters. So let's express the area restriction here. So since this is a rectangle, right, it's easy to compute the area. It would be x times y, and so xy has to equal 216. Once you have your new equation, you solve it for either of the variables. So we can solve either for x or y, and then substitute that into the function for f. So it doesn't matter which one you solve for. Let's just say we solve it for y. So y is 216 over x, and then we're going to plug that in right here. So we'll rewrite f will be 2x plus 3 times, replace the y with 216 over x, and then that simplifies to 2x plus sorry, the recording got cut off right at the end of the last slide, but basically I was talking about simplifying this. So the second term, the 3 times 216 is 648. So now we have our simplified version of f. The next step is to minimize this function, find the absolute minimum. Of this function. Now we also have to determine if there's an interval, a closed interval that's implied. So over what range of x's? So we need to think, and we're thinking about x's because this is a function of x, right? We could have chosen to have written this as a function of y. In that case, you'd need to find an appropriate interval for y. So we need to think about the context of the problem, right? X is one of these dimensions here on this outer rectangle. And what would be the minimum and maximum values that are possible for that x? And the only restriction, remember, was that the total area has to be 216 square meters. So there's an obvious minimum, right? X has to be greater than or equal to 0. But what is the biggest x could be? Now, since it's the area that's restricted, right, we just know x times y has to equal 216. That's what the area restriction is written. Is there a maximum x that could satisfy that equation? Well, no matter how big you make x, you can always find a y that will make the product equal to 216, right? Just take y to be 216 over the x that you chose. So there really is no max for x for this area restriction. So we don't really get a closed interval for this one. It's only closed at one endpoint, right? Our interval is from 0 to infinity. So we'll just have to, we won't be able to completely use the closed interval method, so we'll have to think of the graph of f as a whole. Okay, so for finding absolute max and min, we need our critical numbers. And for critical numbers, we need the derivative. So here's the simplified formula for f. We want to compute its derivative. So for the 2x, the derivative is 2. Now on the next term, carry along the 648, and then take the derivative of 1 over x. And we've seen this several times. If you remember, it comes to negative 1 over x squared. And that came from, let's do that over here. So the derivative of 1 over x, we already pulled the 648 out in front, so we're just finding the derivative of 1 over x. The idea is, before you take the derivative, write that as x to the negative 1 power. Then you can use the power rule to take the derivative. We get negative x to the negative 2, which can be rewritten as negative 1 over x squared. Okay, so there's the calculations for that. And then you can simplify. This is now 2 minus 648 over x squared. So that's f prime. Now for critical numbers, we look at two conditions. Either f prime could equal 0, or f prime doesn't exist. So for equal to 0, just take our formula that we just found for f prime, set it equal to 0, and then we solve for x. So this will give us 2 equals 648 over x squared. If we multiply both sides by x squared and then divide both sides by 2, this gives us x squared equals 648 over 2, which simplifies to 324. Okay, and then x equals, now it's technically plus or minus the square root of 324, but x has to be 0 or bigger, so we throw out the negative square root. And this works out nicely because this is a perfect square. We get 18. Okay, so that is our only critical number from case 1. Now case 2, values that make f prime undefined. Notice that f prime does have this fraction in it that would be undefined if x equals 0. So that's another critical number. All right, so I think we're running out of space, so we'll continue with our number line method now that we have our critical numbers, and we'll do that on the next slide. Here's summarizing what we have. We developed this function f for the total length of fence. We decided we needed to minimize it over x greater than or equal, originally we said greater than or equal to 0, because that 0 seemed like the minimum that made sense in the problem. But notice f is undefined at 0, so I've changed that to strictly greater than 0. Also, in terms of the context of the problem, if x, which is one of our dimensions, if that were 0, there's no way we could have an area of 216 square meters. So x really does have to be strictly positive. And we calculated f prime. We found critical numbers, but notice one of them, 0, is not in the interval that we're considering. So we can throw out 0. So now we're ready for the number line method. So we make our number line. We only have one critical number, it's 18. So we can choose, we have two subintervals. We'll choose our test points. So I can't choose 0, right? It has to be strictly bigger than 0. Let's choose 10 and 20. And we plug these into f prime, and f prime doesn't really factor. We'll just write it as it is. So when I plug in 10, this will be 648 over 100, which is 6.48. 2 minus 6.48 is negative. And when I plug in 20, we'll get 648 over 400, and when you simplify that, you'll see you get a positive. So it changes. We have here decreasing, increasing. And that tells us we've got a local min at x value 18. So we know the graph as a whole, right? It's defined, we're only considering x greater than 0. We know to the left of 18, it's always decreasing. To the right of 18, it's always increasing. So this has to be not only a local min, but an absolute min because of just visualizing the graph as a whole, even without knowing the details about the shape. It has to be an absolute min. And that's good because we were asked to minimize the amount of fence, right? If we were asked to maximize, we would say there is no maximum, right? This goes up to infinity. So now let's answer the question. They asked us to find the dimensions of the outer rectangle. And those were what we called x and y, right? We had this picture where this length here was x, and this length was y. So we've already found the x value, x equals 18. That's one of our dimensions. But we need, what is the dimension y? So if you look back at some of our equations, we had for our area equation, x times y equals 216. And then we had actually gone ahead and solved that for y earlier. It was 216 over x. So now just plug in the x we found to get the corresponding y. So 216 over 18, and that comes to 12. Okay, so the dimensions of the outer rectangle should be 18 meters by 12 meters. And we also know the division has to go parallel to the y, which is the 12 meters, right? If you use the other dimension, you'll get a different length for that central piece. The other question was, what is the total amount of fencing in this optimal design? We had a function for that, right? That's exactly what f of x is. So just plug in the x value that corresponds to our design, which is 18. So the formula for f is up at the top, so just plug in the 18. So it's 2 times 18 plus 648 over 18. Okay, and then simplifying this gives you 72. Now you could get that same answer if you just went back to another version of f of x before we eliminated y. It was 2x plus 3y. So you would take 2 times 18 plus 3 times 12, and that would also give you the 72. Now we need to put units on this. This is the length of fence that's used in total, so that would be in meters here. Okay, and that finishes this optimization problem. We're asked to find the general antiderivative of this function. So notice this function is a sum and difference of 4 terms. So for finding antiderivatives over a sum or difference, you can go term by term. So let's just, so for the antiderivative, we'll use the same letter but capital. So it's capital F of x. And we just start with the first term, 3x to the 5th. That's a power function. So to find the antiderivative, we use the backwards power rule. You carry along the constant 3, and then the backwards power rule, we increase the power by 1 and divide by the new power. And we'll simplify that in the next step. Next term, carry along the constant, and then the antiderivative of x, also a power function, so use the backwards power rule, increase the power by 1, divide by the new power. The 8 is a constant, right? We've seen with constants, their antiderivative is just that same constant times your variable, in this case x. Now the next one, you can carry along the constant, the minus 2, and then we need the antiderivative of 1 over x. So this is one you just need to know, or you can put it on your formula sheet if you're not sure you'll remember it. It's natural log absolute value of x. Okay, so we have here just multiply the constant minus 2 by natural log absolute value of x. That's one antiderivative, but they asked for the general antiderivative. So that's very easy to do. You just need to remember how to do it. You just put plus a constant at the end. And we have it for that one. So we ran out of time in our review. I just wanted to finish by saying I hope you all enjoyed the class and that you got a lot out of it. We spend a long time here working on just mathematical calculations, but when we have time, we would throw in some applications just so you can have some motivations for where it's useful. There are many applications we could go into, and you'll get into more of those in your other science classes, but we mainly here want to give you the tools mathematically that you'll need to apply there. I wanted to mention that we ran out of time before I got to reviewing Chapter 5, but we've done Chapter 5 very recently, so it's more fresh in your mind, and there's not a huge amount in Chapter 5. We only did 3 sections, but make sure you review that on your own. I'll be posting some review problems. You can get some review from that, as well as looking at quizzes and homework problems. So as you're studying, feel free to contact me with questions. During my office hours, I'll always be available to respond to questions or send an email and I'll get back to you. And just to let you know, I'll post the grades in Moodle as soon as I have them done, and that will include all the grades, including your final exam, the average for your homework grade, and your course average. So hopefully I'll have those there by Monday. So hope everything goes well with preparing for the final, and enjoy the rest of your summer when we're done.